The purpose of this video is to examine boundary conditions for the fourth order differential equation. To this end, I will consider a cantilever beam loaded by a force P and a couple of magnitude 2PL applied as shown. I presume that the length of the beam and its bending stiffness EI are given. The coordinates are chosen as usual for the beam problems. Our task is to find the maximum deflection of the beam. So I will solve this problem using the fourth order differential equation. And therefore, I will start with identifying the boundary conditions. In doing this, I will follow two guiding principles. The first principle is when I define the boundary condition, either at x equal to 0 or at x equal to L, I will be looking only at small neighborhood of each point. The second guiding principle is I will have two boundary conditions per point, two and only two. So if I have identified two meaningful boundary conditions, I'm not looking for anything else. So let us begin. At x equal to 0, I see the wall. What is known about the wall, of course, that it constrains both the translation and rotation. In our case, it means that it constrains the deflection or the vertical displacement, and it constrains the angle theta by which the beam may rotate. Now, I see two boundary conditions. It means I'm done with the wall. I don't need to spend any more time here, and therefore I'll proceed to the tip of the beam. At x equal to L, I look at this small neighborhood near the endpoint, and what I see, of course, is the applied force P and the applied couple 2PL, but I need to say something about the shear force and the bending moment. And to this end, all I do is a very basic free body diagram of the small element. So I show here, in addition to the external forces, I show the shear force V and the bending moment M. Of course, both of them are positive. And now I take this free body diagram and I write down equilibrium equations. Some of the forces will, of course, immediately tell me that V is equal to P. And some of the moments will tell me that the couple M is equal to the couple 2PL, because the couple formed by the forces V and P is negligible because this is a tiny element. So the arms for the forces V and P are infinitesimal, and therefore moment equilibrium equation implies that M is equal to 2PL. And that's what I record. M is equal to 2PL and V is equal to P. Now, let us translate the physical boundary conditions into mathematical one. So at x equal to 0, the physical conditions are V equal to 0 and theta equal to 0. This translates into the conditions V is equal to 0 and V prime equal to 0. At the other end, x equal to L, the physical conditions, M is equal to 2PL, V is equal to P, and this translates into the mathematical conditions where we replace M and V by these two expressions. So now we are ready to formulate the mathematical problem. The differential equation, the force derivative of v is equal to 0, and the boundary conditions. 2 at x equal to 0, and 2 at x equal to L. So now the story looks like this. I will integrate this equation. The integration will produce 4 constants, and those 4 constants will be determined by imposing boundary conditions on the function v and its derivatives. Let's see how it's done. So I start with the differential equation. I integrate one time, I end up with C1, integrate this equation once, C1x plus C2, integrate this, I get this quadratic function, and finally the last integration gives me a cubic polynomial, which is expected because the derivative of the function, the force derivative of the function must be 0, and of course the coefficients of this cubic polynomial are unknown. Now I'm ready to go after the constants C1, C2, C3, and C4, and here's what's happening. I impose the boundary condition v of 0 equal to 0. So I take the expression for v, evaluate at x equal to 0. Of course, I get C4 because the rest of the terms are 0. And the first boundary condition implies that C4 is equal to 0. Now I take the second boundary condition at 0, v prime equal to 0. So this implies that the derivative of v evaluated at x equal to 0 is equal to C3, and it must be equal to 0. Now I go to the other end, to the tip of the beam, and here I evaluate EI v double prime at x equal to L, which is C1L plus C2, and this must be equal to minus 2PL. And finally, the fourth boundary condition, or the second boundary condition at x equal to L, gives me that C1 is equal to minus P. Now, I write down the deflection curve. I bring the integration constants determined on the previous slide, and I put it together, and I get this equation. V of x equal to minus px squared of 6ai times x plus 3l. It's probably very easy to see that v is negative. It means that the deflection will be upward. And this upward deflection is because of the couple 2PL. The force P would like the beam to displace downward. So now to find maximum deflection, all I do is I rewrite V, I calculate its derivative, and I observe that for all x's, v prime is less than 0. It means there are no critical points, and it means that there are 2 points that I need to identify. One, of course, is x equal to 0, where v is equal to 0 because of the boundary condition, and the second point is x equal to L. So I substitute L into this equation, and that's the answer I get. So this is the most negative displacement or this is the most upward displacement.